You should always look for ways to optimize your network and improve its performance. As a network administrator, it's your job to increase fault tolerance so your network can function when a component goes down. One of your most important responsibilities is maintaining reliability for employees and clients. In this lesson, we're going to look at several tools you can use to make this happen: load balancing, caching, quality of service, traffic shaping, bandwidth throttling, and port aggregation. Here's a scenario for you. Let's say we have a web server hosting a website. As usage increases over time, the server can't keep up with demand. You could implement a mirrored server and direct some traffic to it, but then all your clients would have to know two URLs, one for each server. This isn't a very elegant solution. Load balancing fixes this problem. Load balancing divides the network load between multiple servers in what's called a server farm and distributes client connections among the servers. Not only does this increase performance by spreading the load, it increases fault tolerance by providing backup servers. In a load balancing configuration, a virtual server running a load balancing service receives a client connection through a single URL. The load balancing service then distributes the client requests between servers so that the various clients each connect to a different server. You can choose to distribute requests equally or direct most traffic to one server, which might be useful if one machine has better hardware than the others. The key point is that the load balancing is transparent to the end user. Clients just connect to the single URL, and their experience on the website is the same no matter which server the load balancing mechanism sends the request to. All you have to do is ensure that each server has the same website content. A storage area network device, SAN, or network attached storage device, a NAS, can take care of this for you. If you want to really enhance performance, you can implement caching. Caching stores frequently used information locally for quick access. When your computer submits a DNS query for an IP address, it saves or caches that information locally. The next time your computer needs to retrieve that same information, it can quickly pull it from the cache instead of submitting another DNS query to a server and going through the whole recursion process again. You can also use caching to improve web browser performance by configuring a special caching server to store frequently accessed information from the internet. For example, let's suppose that your organization is connected to the internet, and the employees in your company access the same websites multiple times a day. So much of this information that's being pulled down is redundant. This wastes internet bandwidth. So in this situation, you can install a proxy caching server to increase performance. The proxy cache server sits here between your network and the internet. And then, instead of connecting directly to the website, the computers on your network connect to the proxy server, and the proxy server goes out and forwards those requests to the actual website on the internet. Then, when that information is returned from the internet, the proxy server saves it in its cache, and it forwards the requested information back onto the client that made the request. Then, when a second client connects to the same website, the proxy server retrieves the information from its cache and sends it directly back to the requesting computer. Another solution that you can implement is quality of service, or QoS. QoS reduces network latency for time-sensitive traffic like voice-over IP, video, and online gaming. Without QoS, the packets for time-sensitive data could be delayed, delivered out of order, or even lost. Remember, a lot of these protocols use UDP instead of TCP, and this can have a terrible impact on these services. For example, latency can wreak havoc with voice-over IP phone calls. If the latency is bad enough, it'll make the call quality unbearable. QoS prevents this from happening by ensuring that time-sensitive traffic is delivered before other traffic. Suppose we have a WAN connection that we use to connect to an ISP. This single WAN connection might be used for many different types of internet traffic, including voice-over IP and video streaming. Without QoS, all this traffic would be sent through the WAN, unprioritized. Imagine what would happen if you were trying to use this link to make a voice-over IP phone call, and then somebody else in the company started downloading a 4 gig Linux ISO image. In this situation, the voice-over IP packets compete with the FTP packets from the large file transfer. Without prioritization, both types of packets are treated equally. Voice-over IP packets are extremely time-sensitive. Delayed or lost VoIP packets can really impact the quality of the call. However, the packets associated with the file transfer are much less time-sensitive. A little bit of latency probably wouldn't even be noticeable. Also, because the file transfer is using the TCP protocol, any packets that get lost or delivered out of order will be automatically retransmitted. That won't happen with the VoIP packets, which use UDP. QoS typically implements two primary features to prioritize network traffic. First, it classifies traffic types. Then it uses queues to create buffers in the router's memories. The queues store low-priority traffic while high-priority traffic is processed. You can decide which types of traffic take priority. For example, it's a good idea to give VoIP traffic a higher priority level on the network than your file transfer traffic. It might help to think of QoS like postal rates in the mail system. Let's say you visit the post office with 2 pieces of mail, a book for a friend and an urgent contract for your business partner. You decide to send the book at the affordable standard rate. It'll take a while to arrive, but that's okay. It's not urgent. But you want to send the contract to your business partner overnight because you need it signed as quickly as possible, so you pay extra for rush delivery. The book will wait in the post office, perhaps for days, while the contract and other priority mail are shipped through. This is very similar to how the QoS classification and marking process works. It can occur at either layer 2 or at layer 3. At layer 2, individual frames are classified and marked. At layer 3, individual packets are classified and marked. But either way, the most time-sensitive traffic is sorted out and addressed first. For classification at layer 2, QoS uses class of service, or COS. Your network switch assigns a value to the 3-bit COS field within the VLAN tag of each frame. This value determines the frame's priority. For classification at layer 3, QoS uses a protocol called Differentiated Services, or diffserv. Each IP packet header has a diffserv field. Diffserv inserts a differentiated service code point value, or DSCP value, in this header to prioritize data flow. Routers forward packets according to the value in this field. If we need to, there are things we can do to refine traffic flow even more. One thing is traffic shaping. QoS uses traffic shaping to modify the flow of traffic through the network. The flow can be modified in response to QoS labels, delaying some traffic to ensure the delivery of other types of traffic. The traffic shaper might perform rate limiting, for example, which restricts the bandwidth available. For example, your ISP might use rate limiting based on the bandwidth that you've purchased. You can also use a mechanism called bandwidth throttling. Throttling restricts the amount of a certain data type that can be sent during a specific time period. For example, you might limit the amount of data that a single customer could download from an FTP server to ensure that one user doesn't monopolize the server traffic. And there's also port aggregation, or PAGP. Port aggregation is a Cisco protocol that lets you combine Ethernet ports to improve the speed of aggregated or related file transfers. And that's it for this lesson. In this lesson, we discussed network optimization techniques. We looked at load balancing, caching, QoS, and traffic shaping. Then we looked at bandwidth throttling and port aggregation.